Hey guys, okay. Now let's welcome this ETA event tree analysis. I'm going to talk about this and describe you with two different systems. With I have one this kind of system and the other this system. So I'm going to discuss both the systems and would be describing all about ETA and how to draw this event tree analysis. These are basically the trees. You got it? So I'm going to do now event tree analysis, and I told you this one is the top down technique. First we see our system. In the bottom up technique we see first our components, and in the top down technique we see our system. So what system we have here? Let's have a look on our system. We have system 1. Okay, this is our first system. We have a power line, okay, and that is connected to our fuse, which is connected to our switch, okay. And what it happens by connecting, what it gives, it lighten our bulb 1 and it lighten our bulb 2. So suppose we have a room in which two bulbs are present, okay, and that those bulbs, they are getting power from a switch, okay. First they are getting power from the switch. Okay, if you say first, so first they are taking power, getting power from the power line. Then there is a fuse, and then this fuse is connected to the switch. Obviously when we open this switch, so then our bulbs will get open. So this is our system. I told you that in top down technique we represent our system. We talk on the basis of our system. We take our system first. We didn't take the circuit behind these bulbs and circuit behind the scenario that is happening, the lightning in the room. So we didn't take the circuits, we take the system. And what's this system is? The system is just an easy one, that we have two bulbs in the room. These two bulbs, we have a switch, we have a fuse and power line. Obviously when we open the switch, the bulbs would get opened, and the switch is being connected with the fuse, and we have power line. So that's basically our system. And what is our top event? We call this thing as our top event. Our top event is reduction of light in room. So we are going to see that what would be the percentage of light in the room. That's how much light is either this if this switch fails, or this switch operating, or this fuse fails, or this fuse operating, or this power line fails, or this power line operating. So what would be the percentage of being these things in operating or failed conditions. Okay, we are going to see when they are failed operating, what would be the consequence, what would be the effect on these bulbs, and how the light in the room gonna be. Either both the bulbs will be operating, or either one operating, or either both fail. So what would be the percentage? We are going, our top event is what is our percentage of light in room. Okay, so let's have a look how we can draw these things. Oh, how we can draw our event tree analysis. So first we have given this system. We say this power line as A. I hope you are everything is clear, no blurring condition is here. The power line is A, the fuse is B, the switch is C, and this bulb 1 we say it as D, and this bulb 2 we say it as E. So this is our system. We got A, B, C, D, E. Okay, the same we can write it in our table. Light in the room. So first power line we have A, fuse we have B, switch we have C, bulb 1 we have D, and bulb 2 we have E. Okay, and what is our top event? What is our last what we are going to find? We are going to find the percentage of light in room, that how much percentage would be there of the light in the room. So let's see. First we have we can say that either all 5 are operating conditions. When these all 5 are in operating conditions, we have a percentage of 100%. Obviously, when these all 5s would be in operating condition, so the light in the room would be 100%. Okay, there would be a shiny room. You'll have a shiny room. And what we say now, we have different possibilities. Different means we have two. Obviously, we have two possibilities, that either the power line is operating or either the power line failed. Either fuse operating, either fuse failed, switch is operating or failed, bulb 1 operating or failed, and bulb 2 operating failed. Okay, I am going to tell you what is happening here. So how is this being drawn? First we do all the operating as here, so it's 100%. Now in the last we draw failed here. We put a line for failed here, and then okay, and then from that failed we have another table of fuse. So we draw, oh, the fuse has two conditions, two possibilities, operating and failed. So that's why we draw operating here and failed here. And from here, from this operating, we see that we have switch, and this switch can be in the operating condition and in the failed condition. So we draw operating, failed. And from this switch, on the other hand, we have bulb 1. We have bulb 1, and the bulb 1 can be in the operating condition or in the failed condition. And the last we have bulb 2. Bulb 2, for bulb 2 we have operating condition, and from that operating condition we have bulb 2 as operating or failed. And if bulb 1 failed, so we have bulb 2 as operating or failed. So in the last column we have 4 possibilities. Okay, we have 4 possibilities, that when our bulb 1 is operating, so we can have our bulb 2 as either operating or failed. And when our bulb 1 is failed, so we have the possibility of bulb 2 to be operating or failed. So you got it, what I am trying to say? That I am trying to say is that when we have, suppose we have 2 bulbs in the room. Okay, so when one bulb 1 is operating, so the bulb 2 can be operating or failed. Yeah, and when one bulb is not operating, so again the bulb 2 can be operating or failed. So that's why it is represented in the way of this. Okay, got it? So now let's come to the percentage, how this percentage can be defined. Now we have, for all operatings we have 100%. Yeah, and we say we have operating, bulb 2 operating, and where it is coming, bulb 1 operating, and switch operating, and fuse operating, and either power line fails. But it doesn't get any effect of failing it, so either this fails, we have all the others in operating condition, so that's why 100%. Okay, now the next is we have 50%. Why this 50%? We say bulb 2 failed, but bulb 1 is operating, so either bulb 2 failed, bulb 1 is operating. So what is we are finding? We are finding the percentage of light in room. So if one bulb failed and other one is operating, so there would be 50% light in the room, so that's why 50%. Got it? And again down here we have bulb 2 operating and bulb 1 failed. So when bulb 2 operating and bulb 1 failed, we have still 50% light in our room. Got it? So these both are the same, it's just that when bulb 2 is failed, bulb 1 is present, so 50% light in the room, and when bulb 1 failed, bulb 2 is present, is operating, so 50% light in the room. Got it? Now the last one is 0%. Why it is 0%? Because we have bulb 2 failed, bulb 1 failed. When both the bulbs failed, obviously there would be no light in the room, so it would be 0%. So no matter what it's coming from behind, either either the fuse is working or not working, switch is working or not working, power line is working or not working, either it doesn't matter. But what matters is if these both two bulbs are not working, so what happens? Suppose we sometimes sometimes, not sometimes, it happens all the time that our bulbs have been fused and they have been damaged or finished, so we replace a new bulb. So if both the bulbs are not working, so also there would be 0% light in the room, there would be no light in the room. And last is the 0%. When it is 0%, it's 0% when we have all the five things failed, so automatically the result would be 0%. When everything was in the operating condition, the result was 100%, and now when everything is in the failed condition, so everything is now 0%. So this was the method, this was the way of drawing this table. I hope you got it. Everything is being cleared, and now we are talking about its probability. So what is the way of writing this probability? That we can write it as probability equals to probability of A times probability of B times probability of C into probability of D into probability of E. So this thing can be written in the form of the overall probability of the system, right, of this event tree analysis. The overall probability can be written as the product of all five probabilities. Okay, so this was all for the system 1. We were talking about system 1. Now the same thing is going to happen in system 2. Let's take another example of system 2. So let's have a look. Now we have a power line again, and that is connected to a loss of power detector. Okay, and we have diesel generator 1, diesel generator 2, and diesel generator 3. Okay, so we have what we are having now, diesel generators. We are having diesel generators. Okay, and 3 diesel generators are present, which are being connected to a loss of power detector and which is connected to the power line. So here we have the power line as A, loss of power detector as B, diesel generator 1 is C, diesel generator 2 is D, diesel generator 3 is E. So 5 things are present. Now what's going to happen? Now we can see that, okay, yeah, what's written here? We have for power line we have 0.99 and 0.01. What is this? These are the probabilities, okay, for good and for bad. Good or bad means when in the operating condition and when in the failed condition. So when power line is in the operating condition, it has a probability of 0.99, and when power line is in the failed condition, it has a probability of 0.01. Same is for loss of power detector. When we have a operating condition, so its probability is 0.999, and when we have a failed condition, its probability is 0.001. And again is for diesel generators. All the diesel generator 1, 2, 3, their probabilities are the same. For diesel generator 1, 2, 3, we have a probability when these are in the operating conditions, we have a probability of 0.95, and when these are in the failed condition, we have a probability of 0.05. So these are the probabilities. Got it? Okay, so now we have given the probabilities, and we have to write it also in the form of probabilities. We have to find the probabilities. So how we can draw our table for this? For first, we say that we have a normal power supply. Okay, so this is our, basically the system is for our normal power supply. Okay, first is power line A. We say our power line as A, loss of power detector B, diesel generator 1, diesel generator 2, and diesel generator 3, and final event. Okay, final event is our probabilities, what we got in the final part, what is our power, what we have in the power for our final power, what would be our final power. Okay, so again we say that when we have all in the operating conditions, we would be having 0.99. Why 0.99? Because our first power line was operating, so that's why we got the power of 0.99. You see, 0.99 is the best one, is the best power. Okay, so we got, when all are in operating conditions, we got a power of 0.99, so we say it as f1 equals to 0.99. And when we have, okay, now again the method of drawing the table is the same as this one. Yeah, so what happens now, we took it as operating failed, and again we took it as good bad. Okay, I have written here good bad, it's just that it's operating failed or good bad, you can say it anything. So from here it comes good bad or operating and failed, good bad or operating and failed, and again good bad or operating and failed, and again from here we got good bad and good bad, operating failed, operating failed. So it's the same that we did in the last time. Last thing that we create from this operating two conditions, and from this failed we also create two conditions. Okay, so again we are doing it here. From this operating conditions we have created, for diesel generator 3 we have created two conditions, that is operating and failed, and from this failed we have created two conditions, that is operating and failed. So we have created two conditions. Now let's have a look how we can write the final event for this. F is our final event, F is represented as our final event. Okay, F2 is 1. Why we say F2 is 1? Because let's have a look, we have diesel generator in the operating condition, diesel generator 2 in the operating condition, diesel generator 1 in the operating condition, loss of power detector in the operating condition, and either power line failed. It doesn't matter for power line to be failed, but we see that others are in the operating conditions. That's why we wrote our final event F2 as 1. Okay, now let's have a look for our F3 is 2 upon 3. Why we say this, that this is 2 upon 3? Because we have diesel generator 3 in the, what it is, in the bad condition, means it is in the failed condition, and diesel generator 2 in the operating condition, diesel generator 1 in the operating condition. So this means that 2 are in the operating condition and 1 is in the failed condition. So for that final event would be 2 upon 3. So this is basically the fraction, that from all three, from these threes we have two that are in the working condition. Okay, and again F4 is missing here. Okay, let's have a look for F4. What is our F4? We have diesel generator in the good condition, operating condition, diesel generator 2 in the failed condition, and diesel generator 1 in the failed condition. So we have again F4 as 2 upon 3. Got it? And F5 is 1 upon 3. Why it is 1 upon 3? Because we have diesel generator as in the failed condition, and diesel generator 2 in the failed condition, and diesel generator 1 in the working condition or operating condition. So that's why 1 is operating and 2 are failed. So that's why 1 over 3. So how we can write this final event? We can write it in the form of fraction, and what this fraction is, that overall 3 generators, we have 3 for the overall 3 generators, total number of generators, and in the numerator we have the ones that are in the working condition. Okay, so we have, for F5 we have 1 only that is in the working condition, and for F3 we have 2 that are in the working condition. So this is the way of writing our final events. Okay, got it? Till here it's okay. I think everything is being cleared for this table. Now what we have another, okay, now what we say for F5. Okay, we have to find out F5. How we have to find out F5? Basically we have to find the probabilities for F5. Now first we wrote it as in the form of fraction, final event. We find a final event here. Now we say that we have defined the probabilities of for operating and good. We have defined the probabilities here. So now we have to find the probability for F5. So how we can find the probability of F5? Let's have a look. Here the F5 is here. Okay, so it was this, and this. Okay, so it was here. Let's see, it was here first. So we have the power line probability sorry we have the power line probability. In the failed, for the failed condition, we have power line probability for the failed condition is 0.01. So that's why we wrote here 0.01. So right, failed, and then it is here good. For loss of power detector, we have operating condition good. For F5, we have operating condition, loss of power detector, we have an operating condition. Okay, for operating condition means the good condition, we have loss of power detector. For our good condition, we have 0.999. So 0.999. Okay, this multiplies, you know, probability is the product of all the probabilities of PA, PV, PC and PD and PE. So next we have, okay, we are done with this, and we are going to do this, diesel generator 1. So we have an operating condition for diesel generator 1 here. For F5 we say it is good, so what we have for good one, we have 0.95, so that's why we multiplied with 0.95. Okay, now we have done with 3. Now the fourth one. Okay, now we say we are here, so that's why this comes here. We are here, we say, you remember, we say for F5 we have only one diesel generator working, that is this one, and the other two are failed, so that's why we wrote 1/3. So diesel generator 2 is failed, diesel generator 3 is failed, so both are in the bad condition. And what we have for diesel generator 2 and 3 for the bad condition, we have 0.05, so that's why we write 0.05, 0.05. I'm getting it, doing it a little bit fast, so I hope you are not missing it out and everything is clear. So when we multiply all these 5 terms, we got 2.4 at the 10 is to the power minus 5. 2.4 into 10 is to the power minus 5. We got this. Okay, and what it is saying now, what we find out, that 1/3 power is always delivered at the end user. Okay, so either one is only working and two are not working. So in that condition, 1/3 is the power that is always delivered to the user. This is basically the power that is being delivered to the user. So 1/3 is the power that is always delivered to the user. So we got this conclusion here. And what is this? This is something a little to explain you, that for power we have 3 chances. Okay, what those chances are, either we got the power as 2/3, we got the power as 2/3, either we got the power as 1/3, or we say that we have no power. So for power we have 3 chances. Either 2/3 power is being delivered to the user, either 1/3 power is being delivered to the user, or either no power is being delivered to the user. Okay, that's all for now. I have completely described this event tree analysis in a great and quite lengthy manner. So I hope everything is clear. In my next video, I'm going to talk about the FTA, that is fault tree analysis. If you want to know, if you want to learn about FTA, you can go to that video. And that's all for now. Thank you.